Hello everyone. So today we're going to talk about net torque. So last time the lesson was about if one torque is acting on an object to cause rotation. This is if two or more torques are acting on an object. Okay. So a couple things to bear in mind. We like and we see lots of situations like this where we have some mass and the mass will have a force due to gravity, and it's often set up in a way like this where that force is perpendicular to the lever arm. And so we don't have to find the perpendicular component of it because it's all perpendicular. And the only force that's causing that is the force due to gravity. So let's talk about that really quick. The general equation for force due to gravity is mass times by acceleration due to gravity. Okay? And so acceleration due to gravity is the 9.81 meters per second squared, mass in kilograms, and so we end with something in newtons. And so that would be our perpendicular force. And so because of that, because before it was torque equals force perpendicular times by r, well, if the perpendicular force is the force due to gravity in these situations, then the equation can be rewrote like that. Okay? So when I look at this, and say, okay, there's two torques acting on this object, but no rotation is going to occur because the mass is the same, which means that the force due to gravities would be the same, and R is the same for both of them. And when that's the case, then torque 1, that would be caused here, would be equal to torque 2. And so they would cancel each other out. And so our overall net would be 0. Now let's write this off here. Here's one way of looking at this. Remember that counterclockwise is a positive torque and clockwise is a negative torque. So if I have this torque right here, it's going to cause the bar to rotate this way. And so that would be counterclockwise. And so we get a positive torque on this side. Now here, this torque's pulling down on the bar, so it's going to cause it to go this way, and so that would be clockwise, so we'd have a negative torque on this one. So we know, because there's no rotation, that the sum of the torques is equal to 0. We also know that the sum of the torques would be a positive torque 1 plus the negative torque 2. Okay. So I'm going to take sum is equal to 0, so I'll put 0 in there. And then plus the negative, I'm just going to change that to negative torque 2. And so then I can add that over to the other side, showing that torque 2 is equal to torque 1. Okay, now here, we're saying in this situation that the net torque is still equal to 0, that there's no rotation occurring, but this side has twice as much mass as before, and this distance has changed there, and so we've made this a smaller distance because the force due to gravity is greater. And actually it kind of bleeds into this, but we really should change this. This should be twice as big as it was before. Twice the size of that force there. Okay, and so we just need to be mindful that in this situation, if the torques are going to be equal to each other, that if we have a greater force of gravity, then we have a smaller distance from that pivot point. And if we have a smaller force of gravity, then we have a greater distance from that pivot point for everything to equal out. Because if this is bigger, then that must be smaller. Or if this is smaller, then that must be bigger for them to all equal out. Okay. So again, in this situation, the sum of those torques, that net, is going to be 0. Now, if we then say, okay, how about we just remove that weight from above? Let's see if we can show both at the same time here. Yeah. How about we just remove that weight and we don't change the pivot point? Now what's going on? Well, the force due to gravity, that perpendicular component of the force, and it's all perpendicular to the lever arm, they are equal to one another again, but the distances are not equal. And so if the r's are not equal, then T1 cannot equal T2. So a rotation would occur. Okay, so how does T1 compare to T2? Well, T1 has a shorter distance with the same force due to gravity, so it would be smaller than T2. In which direction would the beam rotate? This is a smaller torque, this is a larger torque. And so we would cancel out this and still have some left over. So that would be going down, so it'd be a clockwise, so we'd have a clockwise rotation, which would be an overall, the sum of the torques would equal a negative torque. Okay, and this is just a summary of those things that we just barely talked about. So let's go on to our example problems then. Let's see where we at time-wise. Okay. So example number 5. You're at the playground with your younger sister and her friend. They are playing on a seesaw and trying to adjust the pivot point so that it will balance when they are on it. You decide to help them out. Your sister's mass is 56 kilograms and her friend's mass is 43 kilograms. Using your handy tape measure, you find the length of the seesaw. Now, I actually went back and made some adjustments, so follow along with me. If I remember right, I want to say that this was 3.42 meters. And we're not wondering about where we should place the pivot point. We're going to say that our sister is 1.3 meters from the pivot point. How far is her friend? Okay, so we want to know the distance away from the pivot point of the friend. Okay, so if I were to draw a picture of what's going on here, let's see, sister's mass is here and the friend's mass is there. So the friend's mass is less than the sister's mass. Okay, so we have your sister, and then we're going to have the friend. And we know that this distance is 1.3 meters, okay? And just because we know the whole length doesn't mean we're subtracting them. We don't know if the friend is all the way at the end or further in, right? No. Or if the sister is all the way at the end. We don't know that either. So we have two torques acting here. We have torque of the sister and torque of the friend. Okay. See if I can get this to focus a little bit better. There we go. Okay, so we have torque of the sister and torque of the friend. Okay, and we have a force due to gravity of the sister and a force due to gravity of the friend, and that's what's causing that torque. Now we can solve a couple things here to help us solve this. We can look at the force due to gravity of the sister, because that's going to be the mass of the sister times by the 9.81. So 56 times by the 9.81. I'm going to leave long numbers until the very end, 549.36 newtons. And then we can figure out force due to gravity of the friend, which is 43 kilograms, times by the 9.81 meters per second squared. .83 newtons. And then we have, I'm going to keep working over here on this side. We know that torque in this situation is force due to gravity times by R. So torque of sister will be that force due to gravity times by that distance away, the 1.3. Okay? So I'm going to take that, let's see, force due to gravity of sis times by R of sister. And I'm getting a torque of 714.168 Newton meters. Okay, so we have a lot of great information here. Now let's put together the sum of the torques. We know that they're equal to 0 because it talks about them being balanced. And so we're going to say the sum of the torques all equal 0. But we also know that the sum of the torques is going to equal, let's see, sister's going down here, which would cause a counterclockwise motion. So we'll have a positive torque of the sister plus the negative torque of the friend, or minus the torque of the friend. And again, that was equal to 0, right? So then I will subtract that over. So we know that the torque of the friend has to equal the torque of the sister. And we know what the torque of the sister is. So that must mean the torque of the friend is the same, 714.168 newtons. And our general equation, the torque of the friend, will equal the force due to gravity of the friend multiplied by the distance away from the pivot point for that friend. And that's what I'm solving for. I know both of those things, so I'm going to divide that over. Sorry, working small space. So torque divided by the force due to gravity, that will give us R. And so I'll take that torque, the 714, divided by the force due to gravity of the friend. Okay, now, how many two sig figs, 2 sig figs, 3 sig figs, 2 sig figs. So my final answer will be 2 sig figs. So I'll be 1.7 meters away from the pivot point. Okay, there's my final answer for that point. All right, now, a new friend whose mass is 52 kilograms comes and replaces your sister's friend who has to go home and feed her rabbit. Where should he sit? We got to figure out this again for 52 kilograms. So let's figure out that new force due to gravity of the new friend here. So that'll be 52 kilograms times by the 9.81 meters per second squared. So that's a 510.12 newtons. And this situation still holds true. It's still balanced. So the torque of the sister is going to still equal the torque of the friend. So the torque of the friend is still the 714.168, oh, this should say Newton meters. And then we just follow through with this last component. Torque of the friend divided by force due to gravity of the friend will tell us the R component for the friend. And so I'll take that 714 divided by the 510, because that's our new force due to gravity with this new mass. And that gives us 1.4 meters. Okay, so we're right at the end of our time. So when we get back, we'll do example number 6, and then we'll move on to the assignment.